The topic is limits of a function and the limit laws. Um, when we talk about limits of a function, I want to go back briefly to what you learned about functions in algebra class, just to give you the contrast. So I've put up what's really the algebra class view of a function. The algebra class view is that a function is a rule that assigns a unique y value to each x value. You can think of it in terms of input and output. Give me an input, I'll tell you what the output is. That's what a function does. In fact, in the pre-calc unit, we covered exactly that view of what a function is. I've put up just some examples of that. On the left, you can see that we have a graph, and this is a graph of the parabola y equals x squared. It's clearly a function. It's a rule where if I give it the value, oops, looks like I made a mistake already. If I give it the value 2, the parabola gives me, excuse me, the value 4. So so you can think of this graph as essentially defining the rule of a function. On the right, I've put up something a little bit more abstract. There's no particular reason that a function has to be easily graphable. It can simply be a rule. So in this case, we have just a list of values 0, 1, and 2, and I'm implying this goes on for the integers. And then there are just very specific numbers, 10.2, pi, e to the 7th power. These are just numbers that are associated with those integers. You're going to say, well, wait a minute, what rule could possibly give those numbers? And the answer is, it doesn't matter. It doesn't have to be an easy algebraic rule like x squared. It can just be any rule and it's still a function. Anyway, that's what functions do. But this is different from the calculus view of what a function is. So in calculus, what we're able to do is ask a new question about functions, which is not merely what value does the function give when we give it a particular input, but rather what is the tendency of the function. In order to understand that, I want you to take a look at these two functions that I've put up at the bottom here. They're almost the same. I have the function f and the function g. So in the function on the left, y equals f of x, what you can see is that f of 3 is equal to 5. I've put in all the numbers, and when we put in an x value of 3, we go all the way up here to where the curve is, and we see that it has a y value of 5. Now, let's look at the very similar function here. On the right, this is y equals g of x. When I put in 3, if I look at where the curve is, there's sort of a hole in it at x equals 5, there's a hole in it at y equals 5 that looks like where the same value is in f. But for the function g, the actual value of the function of g is 2. So we've written that down here, that f of 3 is equal to 5, but g of 3 is equal to 2. In algebra, that's as far as we would go. But in calculus, that's not the end of the story. Because what you want to do is imagine that you were an ant crawling along this function, or maybe a different ant crawling along on this side. So what I'm drawing is a red ant. This is a fire ant for our friends from Florida. If you were an ant crawling along the graph of y equals f of x, not only would you actually end up at the y value of 5 when you got to the x value of 3, but it would look like that's where you were going to end up. If you were really paying attention to where this curve seems to be going, that's where you'd end up. Now, look at the function on the right. Same ant, same fire ant, don't sting me, crawling along the function, and it says, where am I going when I get to x equals 3? It looks like I'm going to get to 5. And then, somehow, miraculously, the function just completely shifts gears and its value is 2. So your conclusion about where the function would end up is wrong in the case of the function on the right, but that doesn't mean there's nothing we can say about the fact that it looked like it was going to 5. And the way we quantify that in calculus is we write that the limit as x approaches 3 of g of x is equal to 5. Now in this case, in the function on the right, we would say that the limit as x approaches 3 of f of x is equal to 5. Because in both cases, the ant would have concluded that it was going to end up at a y value of 5. So this statement, the purple statement, is true about both functions. It just so happens that the function had a different value had two different values at x equals 3. When in the case of the left function, it was actually equal to 5. In the case of the right function, it was equal to 2. So the point is, the green value is what the function actually equals at x equals 3, while the purple value, what we call the limit, is where the function seems to be going near x equals 3. This concept is what we're introducing in calculus, and frankly, it's what all of calculus is based on. Now, obviously, this is a very intuitive understanding of what the limit is, and we're going to get more into the calculations. But just understand, this is what we're talking about when we talk about limits. We're talking about the tendency of where a function appears to be going near a particular point. I want to just be very precise about what the notation is that we use when we talk about limits. We write the limit as x approaches c of f of x is equal to L, which is how we pronounce it. We write this expression and we pronounce it, the limit of f of x as x approaches c is equal to L, or the limit as x approaches c of f of x is equal to L. It's kind of a mouthful. It gets a lot of stuff into the same expression, but that's what we mean. So that's the notation that we use for the concept that you saw on the last screen. In this expression, we refer to L as the limit. That is actually the limit of the function as x approaches c. C doesn't really have a good name. I've never seen a good name for it. I refer to it as the approach point. So in this example, I would say the approach point is C. Going back up here, I would say that in these examples, the approach point is 3. So in both cases, the approach point is 3. The limit is 5. And let's go back here. So the last thing to note, which you can see in the previous drawings, is that in this expression, this expression up here, L is a y value and C is an x value. So assuming we're talking about y being a function of x, obviously if we change the variables, then we'd have to switch this around a bit. But if we're talking about the typical y as a function of x, then L is going to be a y value and C is going to be an x value. Just to put it in terms that you might have seen, so if I say, for example, that that's 3 and that's 5, as in and let's call this f of x, what we would say is that if I'm making the statement the limit as x approaches c of f of x is equal to 5, we would say that c is equal to L. We would say that c is equal to 3 and L is equal to 5. So as you can see, 3 is an x value and 5 is a y value.